Workshop 3 is about carboxylic acid derivatives. Before we get started, though, we haven't talked about amides and alcohols just yet, but pause the video and try and figure out how this mechanism would work. Okay, so even though these are two functional groups we haven't talked about combining yet, the mechanism is going to be very similar to ones we talked about in the last workshop. So with catalytic acid, we're going to protonate our carbonyl. Then we will have our methanol come in. Again, you could easily draw the carbocation version here. At this point, we have our protonated methanol as a nucleophile, adding at that carbon position, our alcohol, and our nitrogen compound. Here we can see an intermolecular hydrogen transfer where that nitrogen uses its lone pair to pull off the hydrogen of our nucleophile. Then we can have our oxygen push its electrons down, kick out our amino compound that's going to be a great leaving group. If you look at our products from the top of the reaction, you can see we have a protonated amine. So our last step could be using that kicked off leaving group to pull one last proton off of that oxygen, giving us our ester. So you can see that the mechanisms are pretty similar. You just have to get used to, do we have a base? Is it a nucleophile? Can it attack the carbon position of the carbonyl right away? Do we need to protonate first? And then before we can push down, you want to make sure you have a good leaving group. So a couple things that we talked about last time as far as esterification reactions go. You can also do an intramolecular esterification. If that's the case, you get something called a lactone. You can see that there's our ester in a ring. It usually works great with 5 or 6 membered cyclic esters. Sometimes predicting products can be a little tricky if they give you the molecule that the carboxylic acid and the alcohol can react, but we know that those two functional groups will give you an ester. Just so happens this one's intermolecular. You can do the same thing with nitrogen compounds. So if you have two dicarboxylic acids and amines, we can combine those. We get our carboxylic acid and our amino salt. Those, after heating up, we can turn those into an amide. And the same thing we just saw with a lactone, we can do with a amino acid. Again, the amino group on the left, and acid group on the right. And when those cyclize, it's called a lactam. If you haven't talked about that in lecture, I wouldn't worry too much about it. So a couple other reactions we're going to talk about with carboxylic acids before we move on to the derivatives. Any strong reducing agent, this time lithium aluminum hydride, can turn a carboxylic acid into a primary alcohol. Doesn't matter where it's located. Know that this is very reactive, so if you have any other groups that can be reduced in your molecule, they will probably reduce them as well. The last reaction we'll talk about with carboxylic acids is using reagents we talked about last time and making acyl chlorides. And this one's going to involve making an alpha bromination product. So we'll start with a carboxylic acid. We can use our Br2, and I've seen either trace phosphorus or trace PBr3 as a catalyst and give us our alpha brominated product. We'll go through the mechanism, but the steps of this is pretty familiar. So the first two steps I'll go over pretty quickly. Our first step is going to be adding a halogen, making an acyl chloride, or in this case an acyl bromide. So we reviewed this mechanism in the last workshop. Go ahead and refer back to video 2 if you have questions on it. Bottom line will result with an acyl bromide. This is going to happen a little bit faster or a little bit easier than with a normal acid. And here on our right we have our nucleophilic intermediate. This step here is going to involve finally adding the bromine to the alpha position. At the top, you can see that it's going to add across the double bond. Alpha position, remember this is a keto-enol tautomerism, so that position is actually a little favored. So I'll have the bromine in the alpha position. This last part here is the part we'll go over in more detail, where we have our dibrominated product and another molecule of carboxylic acid that can come over, have a complicated hydrogen transfer, giving us our alpha brominated product on the left, and our catalyst to continue the reaction back in step 2. So let's talk about this reaction a little bit. It starts by having our carboxylic acid act as a nucleophile, pushing electrons out onto that oxygen. Here you can have 2 resonance structures. The important parts here are the oxygen with the minus charge at the carbonyl that was attacked by our carboxylic acid. This is then going to allow the bromine to leave. We'll push those electrons back down, kick out the bromine. This part probably doesn't seem very intuitive, but remember, we just kicked out bromine. We have an electrophilic carbon and an oxygen that's not very happy right now. So we can have bromine come right back in, push those electrons onto the oxygen. And at this point, this should remind you of something that looks like an anhydride. But remember, our end product here is going to be our alpha brominated. So the top portion of our molecule there is going to be our alpha brominated product. And the bottom part has just become a great leaving group with that bromine added to that part of the molecule. So here we actually have a 5-membered transition state where we transfer the hydrogen from our great leaving group, giving us our alpha brominated product on the right, and our brominated product on the left that can then be used back again in step 2 of this reaction. So a little bit of a tough reaction, but this transition state part is the bulk you need to remember, and it should remind you of our addition for chromate reagents with alkenes, so not too complicated. We'll start talking about carboxylic acid derivatives, with our carbon-13 being a little bit lower than what we saw in the past for our ketones, acids, and aldehydes. These are going to be a little bit lower, sort of in the high 160s, low 170s range. So something to keep in mind if you see the carbon-13 NMR for that. Also looking at acidity of the alpha hydrogens in these molecules, we can see that they increase as we're going to the right, as we go to more reactive compounds, acyl chlorides that we talked about, as well as noticing as we go to the left, we're dealing with electron donating groups that are going to decrease our acidity. So alkyl halides, for nomenclature, our carboxylic acids will go to ill halides or oil halides. Carboxylic acids will be carbonyl halides. First one, we have pentanyl fluoride, so we have a 5-carbon. If it was an aldehyde, it would just be pentanal. So just changing that last part to signify we still have the double bond carbonyl as well as a fluorine group coming off of that carbon. Next one, cyclohexane carbonyl fluoride, just a cyclohexane group with that 1 carbon, again having the same functionality as our previous one. 3-methylbutanol bromide. Pause the video now and try to draw this structure out. Okay, so you should be saying butanoil is going to be our base chain. At position 3, we'll have a methyl group. Here we have a bromine instead of a fluorine coming off of our carbonyl. So nomenclature not too bad. Reactions, again, these are going to be very similar to what we talked about before. We have a very reactive molecule. We have a nucleophile. We can have that nucleophile attack at the carbonyl position, create a carbanion. We already have a great leaving group with our chlorine there. Oxygen can come push those electrons back down, kick chlorine out. Our last step could be another molecule of water or a chlorine coming in and taking that proton off of our OH group, and now we're left with our carboxylic acid. If we take alcohols and alkyl chlorides, you should see the same mechanism, except we're going to make esters now, right? We just added OH2, now we're going to add OH with an R group attached to it. Usually you see these with some sort of base in a hydroxide or a pyridine to help neutralize the HCl that you make. So here would be a reaction. We start with our acetyl chloride, propanol, and a tertiary amine. And our tertiary amine doesn't participate in the reaction, it just as a scavenger to help neutralize the HCl, and we get our ester. Mechanism. Same thing as before, right? We're going to use our alcohol as our nucleophile, kick out the electrons onto the oxygen. electrons will get pushed right back down, kick out the chlorine, and that chlorine can then come and pull off that hydrogen, and we're left with our ester. So again, hopefully you're seeing a lot of similarities with all these mechanisms, just making sure we can recognize what's the nucleophile, what's the leaving group. For reduction reactions with any acid chlorides or alkyl chlorides or alkyl halides, all right, our any organocuprate is going to turn it into a ketone. Lithium or Grignard reagents are going to add twice. So we're going to lose our carbonyl functionality and you'll be left with a tertiary alcohol. Remember that our acid workup always follows Grignard's. That's the proton that eventually adds to your original oxygen from your carbonyl. Two more, if we have lithium aluminum hydride here, we're going to make a primary alcohol. Remember, we're just adding H- to that carbonyl position. And the last one is a unique reaction, a new reagent. It's a highly branched lithium aluminum compound where we have starting with some type of acyl halide, and this reagent, specifically the one shown here, is nicknamed dibol, and it turns acyl chlorides into aldehydes. We'll go through a lot of these similar reactions with other functional groups, other carboxylic acid derivatives, so be sure to keep these in mind.